All right, so what about this guy here? We've got this function that's drawn for us. Should I make that bigger? Can everybody see that okay? Is that better? We've got this function that's drawn, and we want to try to find the domain and the range using all our different kinds of notation, and we also want to identify the end behavior, right? So what do you think? What's the domain going to be for this one? Ideas?
0.
What's it going to be?
0.
Not following that. So the domain, remember the domain is the set of all the x values, right? So how do we think about this? You can think about this sort of mathematically. The question we're asking is, what are the x values that we could input into our function to get that graph? In other words, what x values work for the graph? There's a couple ways you can if you're given a graph of a function, there's a couple ways you can think about the domain. You don't have to use all these. If one of these clicks for you, then great. But if not, you can ignore any of these. One way we do a lot of this kind of thing in my, like in calculus and in my physics class and things like that too. And one way I always talk to people about this is if you imagine the x component of each of these points, right? Domain is an x issue. That's the horizontal part, right? So if we were to shine a light vertically from infinitely high above and infinitely far below, if we were to shine a light up on this thing, and then we're going to cast a shadow onto the x-axis, where would the shadow be? Because that would be the domain, right? Those are going to be the x values of the function. Okay, that's one way to kind of think about it. I don't mind the little ant analogy that I use sometimes. It sounds kind of dorky, but I think it works okay. If an ant is crawling along this function, it's just like asking the question, how far to the left could the ant crawl and how far to the right could he crawl? Okay, that's another way of thinking about the domain. We're only seeing a small portion of the graph, but it goes forever, doesn't it? Right? So what do you think? Is there anything to stop the ant from, as he walks backwards along this graph, going left? And he's going to keep going down, right? But he's still going to be progressing to the left as he walks down. Agreed? See what I'm saying? So is there any limit? Is there going to be some boundary to the domain on the left? There's not, is there? Does that make sense what I'm saying? There's no reason. It's not like, for example, a function. If I were to graph, well, we'll see one in a second that'll be different. Okay, that'll be very different from this. He could keep on moving to the left, and he's going to keep on going down, but there's nothing to stop him. Same thing to the right, correct? There's nothing up here to indicate that it just goes on infinitely far the way it's going, right? If he moves to the right, he'll keep moving down, but he'll keep moving to the right. So what does that imply about the domain then? What do you think? Dante, what do you think the domain's going to be then? I'll give you a choice. Here, you can take your pick. Let's look at the... Let's look at interval notation. What do you think? Which one of those is going to fit that best? The x values.
The very bottom one?
Bottom one, sure. Right? It's unlimited, isn't it? It's going to go forever in both directions. So then the corresponding inequality would be what? Bottom one, yeah. Okay. And then the set notation, well, same thing, right? Just enclosed in set brackets. Okay, let's look at the range. What about the range? Now, range is the set of x or y?
Y.
Set of y. Okay, so now we're looking at the vertical progress of the ant, right? What's the lowest that the ant could go? Well, is there a bottom limit to how far down he can go? No. He's going to go, if he walks either to the left or the right, he's going to keep on going down, right? So there is no bottom limit to the range. What's the highest the ant could go? 0. And he actually could step on a y value of 0, couldn't he? Right? So what do you think? What's going to be, Wally, what's going to be the interval that best fits that? If he can go forever down, but he can only go up to 0. Middle. Yeah, that's it. Because look what that says. The middle one says that the left, or not left anymore, right? Now we're going up and down. So the bottom boundary is going to be, there is none. right? It extends forever. The top boundary is at 0, and we get the square brackets because it includes 0, right? Make sense? Okay, let's see. So what's going to be the inequality then that matches that? Top one, yeah. And it's important that we get that equal sign in there, isn't it? Okay, good. You guys have got this. It's getting easier. Okay, what about the end behavior? Now let's look at that. So remember, the end behavior, that's the behavior way out to the right or way out to the left. So when we're talking about end behavior, it would only make sense for us to start the sentence when we're talking about end behavior. It's got to be one of these two things. As x approaches positive infinity, or as x approaches negative infinity. That's what end behavior means. We want to know what's going on infinitely far that way or infinitely far that way. Okay? So if we see any other choices, we would automatically know that those choices are bogus. They're not going to work. Like well, I guess we don't get that. So if we were to have had a choice that said as x approaches 0 or something, that doesn't make sense as end behavior, right? We got to be going infinitely far to the left or infinitely far to the right. So what about let's take the top one first. As x approaches negative infinity, in what direction is the ant walking? As x approaches, x is a horizontal variable, right? So we're going left, right? We're going infinitely far to the left. As the ant walks infinitely far to the left, what's he doing vertically? Going infinitely far down, isn't he, right? So what's the answer going to be for that end behavior question then? As x approaches negative infinity, f of x, which is y approaches negative infinity. It's going down, right? Okay, what about as x approaches positive infinity? Same thing, right? As the ant walks infinitely far to the right, he's also plunging infinitely far down. So, negative infinity. Okay? We got it. All right. Next issue comes up on your assignment. Okay, what if we have a situation where the domain has been shortened? Okay, it's been limited. So something like this. For this function, for the given function and the domain that's given, select the graph and identify the range. Okay? So we've got the line f of x equals, that is a line, isn't it? Right? Doesn't that fit the form y equals mx plus b? Right? We got the function, I'll write it a little bigger so everybody can see it. We've got the function f of x equals negative 1/2 x plus 1, right? Okay, so that's a line. What's the slope of the line?
Down 1.
Okay, so negative 1/2, right? It fits the form mx plus b, right? So there's the slope. What's the y-intercept? 1. So positive 1. So if we were to graph this thing, I'll just graph it on this one, okay? If we were to graph the line itself, we would know that we would, well, I guess this is going by 4s, so it's a little hard to graph, but there's gonna be maybe the x-intercept at 1, and it's gonna go down by 1 and over by 2, so it's gonna look something, kind of like that, if I graph the line. But we're not graphing the whole line. Look at this part right here. There's the domain. They're telling us that for this function, the domain is going to be restricted to only the x values greater than or equal to negative 4 and less than 4, right? So we got to go in and erase all of that infinite line except the part on our domain. Does that make sense? So negative 4 is right there, so I guess we'd go from there up to positive 4, and then we got to make sure we get the endpoints right. What kind of an endpoint would I have on the left if x is greater than or equal to negative 4? Okay, good, so it's going to be solid. And then on the right, if it's just less than 4, open. So that's the one that should be our answer, right? We just gotta find that one. Well, I didn't draw that. Theirs is a little better than mine, but you get the idea, right? I didn't quite have the slope right, but that's the one, isn't it? Okay. Okay, so we know it's this guy. Now we want to know, so check. Okay, got it. Now we want to identify the range. Well, how do we find the range? Do we want to probably, looking on the graph, is that going to be the most effective way of doing it? We maybe could get by with it this time, but those endpoints aren't the most convenient endpoints in the world. How could I find out, if I know what the function is, how could I find out what, this is going to be convenient. So there's my function, right? How could I find the values of those endpoints, the y values? This is a really important concept. So here's my function, f of x or y equals negative 1/2 x plus 1. Here's our domain. What am I going to do? How can I find those y values? Because that's really what I want to do, isn't it? If I could find out what those y values were, then I'd know what the range was. Yes, ma'am. Good, good. That's what a function does for us, right? It's telling us that our function it's based on the input variable x. So if I want to know what the outputs are going to be, I got to plug in values for x, right? And this is the recipe or the equation for finding those values. So let's take, for example, let's take the left endpoint. That's just going to be what we get back when we plug -4 in for x, right? So that's going to be negative 1/2 times -4 plus 1. Well, what is that? What's negative 1/2 times -4? Negative times negative is positive, and we get positive 2, don't we? So we get 2 plus 1 equals 3. Okay, so this is telling us when I put in -4, I get back 3, right? Okay, so that gives us the endpoint -4, positive 3. Okay, let's go over and look at the other endpoint. The other one is at positive 4. So f of positive 4 is going to be -1/2 times positive 4 plus 1. What's -1/2 times positive 4? -2 plus 1 is -1. So that's telling us that the other endpoint is at positive 4, positive 1. -1.
And it's
Oh, that's supposed to be negative, isn't it? Whoops, sorry.
it should be 3 and...
Yeah, that should be -1. Whoops.
No, you can't have 4, it's not equal to 4.
Okay, you're right. It's not equal to 4. So that's telling us, but that's the location of the open circle, right? So if we go down to our graph now, oh man. So if we go down to our graph, there's our graph. Right now we know that the left endpoint has coordinates -4, positive 3, and the right endpoint has coordinates positive 4, -1. We want to know the y values, right, to find the range. So what's the lower boundary of the y values that the ant could have? So if I look at this from the side, what's the y value of the bottommost point? Well, okay, -1. Now you can't stand there, right? But doesn't that just mean that when I want to find the range, I'm just going to put an open bracket on the bottom value? See what I'm saying? The ant can't, he can, it's like walking towards the door. He can get down, he approaches a value of y equals -1. He can never quite get there, but that's the limit for him, right? He can't go any further than that. Does that make sense? So the bottom limit of the range is y equals -1. What's the highest y value we can have? 3. See what I'm saying? Okay. What kind of boundary should I have there? Whoops. Where? should be squared because it includes that endpoint is solid. So we actually can stand on the point where y equals 3. See what I'm saying? Now, we could have gotten that from the graph, but we just needed the function to clarify what those y values actually were at the end, right? Okay? Questions on that? Okay? Let's go. Okay, last issue. And this is it for this. This is a big section, but this is it. So what we want to do now is we want to practice taking some information and turning it into a linear model, right? So before we do that, let's kind of remind ourselves. Let's look at a quick little sketch of something here. So really, arguably, the most important thing that math does for us is it provides a model. If you want to, for example, we talked about, I can't remember what I talked about with what class, but in physics, we use math to model the real world. Did we talk about shooting a basket or firing a bullet in here? Yeah, a couple days ago? No, didn't. Okay, well, so if I want to, for example, if I'm gonna shoot a jump shot, what I've got to do is I've got to have some kind of mathematical model. If I want to be able to calculate how to do that, I would have to know with what force and at what angle should I shoot the ball so it's going to end up, when it gets to the goal downrange a little bit, it's going to be 10 feet high, and we could calculate that mathematically. And when you go out and shoot a bunch of jumpers in practice, kind of what are you really doing? Well, you're training your brain to have this mathematical model kind of ingrained in your brain, so you know that if you're a little further away, you know how to adjust your shot, for example, right? But we can do that mathematically. If we want to know, let's say we want to fire a gun, and 600 meters down range, we want to hit a bullseye. Well, if we know the muzzle velocity of the bullet, and we know some of the parameters, like if there's any wind, we can actually calculate exactly where you aim this thing to hit a bullseye, right? If you want to know what the weather is going to be, you can take a boat out this weekend. You look at the long-range forecast, and where's that coming from? It's a mathematical model. These meteorologists are just collecting data points from all over places and putting it into this big equation. Literally, that's all it is. And it's going to spit out some values that make predictions about what the weather's going to be. So mathematical modeling is everywhere. It's probably the most important thing we do. One of the easiest ways to model stuff is linearly. So let's just talk about this for a second. We know that if we've got a line, and let's say we're going to use this line to model something. Let's say we're going to use this line to model how fast the interest in your savings account is growing or something like that. Okay, probably if we're going to do that, we're going to usually start at this value right here. We're going to start at x equals 0, and maybe we're going to move out, maybe these are years. And so after 1, 2, 3, 4, 5 years, we want to make a prediction how much money is going to be in the bank, because y is going to represent, in this case, the amount of money in your account. Agreed? So what would we call the y-intercept in this case then? If this is time in years, this is at year 0. What does that mean? Starting point, right, or the starting amount, right? The initial amount or the starting amount. So this is the money that you've deposited in the bank. Does that make sense? As we move down the line, however, it's going to grow based on the slope of that line, and we're going to get back values that are going to be predictions of how much is in the bank, right? So the slope we would call the rate of change of the amount, and the y-intercept in this case is just the initial amount. And that's really, those are the two components of a linear model. Starting amount and how fast is it changing. Okay, so having said that, let's look at this example. So Joyce jogs at a rate of 1.5 miles every 10 minutes. So that's telling us that it's 0.15 miles per minute. is her rate, okay? For a total of 30 minutes. So we want to find the model that represents the real world situation. So presumably we're just trying to we're trying to predict how far is Joyce going to have run after so many minutes, right? What do you think? So what's her starting value?
0.
Yeah, she's starting from the starting line. In this case, it's 0, isn't it, right? So we don't have to worry about a y-intercept, right? The starting value is 0. So all we need is a rate, right? What's the rate going to be? You always want to look, a rate is always going to have units that are going to be a fraction, something per something, right? Yeah, so it's going to be 0.15 miles per minute. That's our rate, isn't it, right? And we're measuring time in minutes, right? So what's that going to mean for our answer then? We're going to multiply the rate times x, or probably t in this case. Maybe we'll use t instead of x. But don't we just get back that? The rate times the variable? That's it, right? That's it. Now what if we change this a little bit? What if we said, okay, next time Joyce is going to start, say we're measuring the distance from her house, and next time she starts half a mile away from her house, she starts on the run. How would I have to change the model?
You would start at what happens to the y-intercept.
Okay, so then I'm going to have to add a starting value, aren't I? Right, so we'd have to add to this. We've got 0.15t plus 0.5. And a lot of times people will even put the starting value first if they want it, either within that. Okay? All right, so what's the domain going to be based on the description? What does this tell you about the independent variable, normally the x variable, we call t this time. What's our input variable? Okay, the time in minutes that she's been running, right? That's what x, or in this case t, corresponds to, is the time she's been running. So what do you think? What's our domain? What are the values of t, or like x, that would make sense for this model? There's a really key part of that description of the situation there.
Greater than or equal to 0, less than or equal to 30.
Yeah, there it is right there. She's going to run for a total of 30 minutes, and then she's done, right? So after 30 minutes, this model doesn't apply anymore, right? So the domain then has got to be so the domain would be which one of those? Well, that's kind of weird at the bottom. I don't know why it's showing up like that, but it's that one, isn't it? Right? Oh, what? What's going on here? A different question. Let's just do that one. I don't get this. This computer's having an issue here, but it should be the bottom one, shouldn't it? Anyway, if I write it out, it should be 0 to 30. Why the square endpoints?
Because they're going to be closed circles on your graph.
Because they're closed circles on my graph. And she is at the starting line at 0 minutes, right? She's there, that counts. And she finishes when the clock hits 30 minutes. So she runs for a full 30 minutes, right? Okay? All right, I think we're good. I think you're good to go. You can, if you want to go through, I mean, there's just some more examples like that. You can go through them if you want to on the interactive lesson, but I think we're good. How much time we got?
18 minutes.
18 minutes. Why don't